Welcome to the Adaptive Array of Power-Efficient Nodes, VXLAN, Part 2. Some new hardware has been added for the purposes of this lab. Completely messing up the home lab is also an obligatory step of the process. A simple underlay has been created for the purposes using the IP address 10.222.222.1 and 2, respectively, creating a simple VXLAN configuration with a VNI of 2220022. Also notice that the bridge VLAN ID is different for each of the switches. The respective VXLAN VTEP devices are added. For hardware offloading, the VTEPs must be statically defined. Notice that the flags RH are present, signifying the VXLAN is running in hardware. Exploring the switches from the cluster interface, one can now observe that the VXLAN configuration has been detected by the cluster fabric. Now configuring the switches. As the VLAN does not previously exist, it is marked as added by PVID. The ports for the servers. Breed is added as a VLAN tagged port, and for lithium, the port is configured as a native VLAN. Configuring the network devices for the servers. Lithium uses an untagged port, and Breed uses a VLAN tagged port. Utilizing hardware offloading, near wire speed performance is achieved. For our next lab, the goal is to achieve hardware-accelerated VXLAN between a Linux host and a switch. Such configuration will allow the hypervisor to use the VXLAN directly in the cluster fabric. The underlay is configured with an address of 10.222.200 with .1 for the switch and .2 for the node. Adding the VXLAN configuration with a VNI of 2222011. The VXLAN is also bridged to a VLAN ID of 695 on the switch. Adding the VTEP interface. The interface is statically bound. It can also be observed that the switch is reporting the H and RH flags, signifying that the VXLAN is now running in hardware. Now it is time to configure the VXLAN on the Linux server. A similar configuration is added here. The other Linux server will run an untagged interface. This VLAN bridge interface is here added to the switch. The Linux server is configured with an untagged network interface and an IP address is added. For our purposes, the VXLAN interface is added to a Linux bridge. This, in turn, will allow virtual machines to utilize this interface. For these test purposes, the bridge is also given an IP address. After VXLAN connectivity between the servers has been achieved, it is time to run some performance tests. A near wire speed performance of over 9 gigabit is achieved with an MTU of 1,500. Optimizing the MTU and enabling jumbo frames. Inching the performance even closer to wire speed with 9.8 gigabit bidirectional performance. Next are some experiments with the MikroTik CCR 2004 Smart Network Card. The card features an ARM CPU with 4 cores running at 1,500 megahertz and 4 gigabytes of RAM, alongside 2 SFP28 ports, each supporting up to a theoretical 25 gigabit of performance. Only testing will show what the card can actually deliver. The card is here seen attached to the server, lost, and provides 4 virtual network cards, PCI Ethernet 1 through 4. The first test will run one of the ports in pass-through mode. In theory, this should give as close to wire speed performance as possible. Notice the CPU load on the card as the various tests are run. The NAPI monitor, bottom right, also shows the load on the server, experienced via the driver. Changing to jumbo frames to evaluate the performance. The card seems to achieve close to wire speed in certain configurations. However, a noticeable difference in egress and ingress speeds can be observed. Now for some VXLAN testing. As the card does not support any hardware offloading, the translations will have to be done entirely by the processor. Firstly, configuring a simple VXLAN underlay. Then configuring the various VXLAN overlay networks. For the CCR, the virtual PCI Ether 4 is bridged with the VXLAN. For the CRS, the hardware accelerated bridge is used. As for these experiments, the servers will not do any VXLAN. Thus, Breed is configured with a trunk interface, and Lost is configured as a native untagged port and using one of the virtual network devices provided by the CCR 2004. Also, keep an eye on the resource monitor as the tests are run. Receiving, the card reaches acceptable speeds. However, for transmitting, a clear bottleneck can be observed. Increasing the number of parallel threads pushes the card close to wire speed. While both the operating system driver and the processing unit of the card experiences significant load, allowing certain configurations and parallelization, the card is capable of reaching very close to 10 gigabit VXLAN traffic. Stay tuned for Part 3, where the results of these experiments will be put together, and hopefully a leaf-spine network will manifest, all with proper cluster integration, of course.